In this tutorial for Explorer, we're going to generate linear regression workflows, including multiple linear regression, the boosted form, and multivariate normal regression and the boosted form. So let's get started. I have Explorer open. So the first thing you want to do is add an Excel. So just click on a red Excel icon. And then you can't really do anything with this until you add other icons. So let's go to dependency for regression. And here's linear regression in the boosted variant. So let's add a feature selection icon. And then linear regression out here. And then the boosted regularized form of it here. And then we can start connecting. So click on link, then drag it to feature selection. Click on link, drag it to linear regression. And then if you drop one of these lines on something that you can't, you'll see a red outline of the icon, so you just can't. So let's drop that there. We haven't imported any data yet, so obviously there are reminders showing here. So we can do that now. So let's import the retinol data set. So this is the data file folder in your My Documents for Windows where the data are installed. Double click on retinol and you'll see the data in the spreadsheet. There are 14 variables, 314 observations, 3 of which are categorical. And now let's go back to workflow. Let's select the features that we want to use. So this is multiple linear regression, so you can only select one continuous outcome variable. So let's select fat. And then with some of these predictors, we'll try to model fat or predict fat. So let's use age. And by the way, let's select all the categorical features. So over here you want to select discrete features. And then let's select calories in the diet, catalyt index, fiber. We can't select fat because it's already selected as a dependent variable. Alcohol is kind of a strange variable because there are a lot of zeros, and then there's some people with real high values. That's alcohol consumption for the week, so let's leave that out. The plasma cholesterol, let's click on that. And then beta, these are more outcome variables, so we can select them. In fact, let's not, let's leave it like this. Now, however, let's change that and predict let's predict blood plasma beta alanine or beta carotene levels. So these are blood markers. These top 2 are based on questionnaires and the bottom 2 are plasma concentrations. So let's use these then to predict the plasma concentration of beta carotene in the diet. So we're using age, the categorical variables, catalyt index, calories, and fiber in the diet as well, and then cholesterol based on plasma. Now click on apply. And now those are the features that are selected for this linear regression run. Now you can go over to linear regression and edit the parameters. So let's just leave these default parameters there. Now for boosted regularized regression, there's not really anything that you can select. It's kind of a blank option pop-up, so let's leave that. We said we were going to perform multivariate normal regression, so we need a different type of feature selection icon. And the idea here is that X selects X variables and one Y, and then here the feature selection icon for multivariate normal regression has 2 Ys in it. So we need to connect the data icon to the feature selection icon for multivariate normal regression. And then we're going to need the MVN reg icon to do the multivariate normal regression, and then the boosted form, and then connect these. So we're connecting the yellow feature selection icon to the analysis icons. By the way, analysis icons are all colored green, and then feature selection icons are all colored yellow. And there's one, as you can see, there are 2 rather red icons for data inputs. now we haven't selected features from multivariate normal, so let's select those. Now these are outcomes, so let's try to predict two of the plasma concentration forms of beta-carotene and retinol in the diet. And again, let's use age, catalytic index, calories in the diet, fat in the diet, fiber in the diet, and we'll leave cholesterol out. And let's use the categorical variables again. Now remember, Explorer will generate k-1 binary vectors for all levels of categorical variables. So sex or gender is a two-level variable, 1 and 2 for both genders, and then Explorer will generate one binary vector of zeros and ones to pick off the second group, because the first group will be the reference cell. And then smoking status has 3 levels, so there will be 2 binary variables, with the first level used as the reference cell. And then vitamin use is also a 3-level categorical variable for which Explorer will generate 2 binary vectors to pick off the second level and the third level, whereby the first level is the reference cell. So we've selected the 2 dependents, and we don't want any interactions here. Although this is, we use the discrete, so we need to select the continuous outcomes. If one of the advantages also of Explorer is that if you select a categorical variable for discrete, it won't make k-1 binary vectors, but rather 3 vectors for 3-level categorical variables, these 2 specifically, smoking status and vitamin use. And then for 2-level, it'll generate 2 levels. Whereas when you have used discrete variables for predictors in linear models, you commonly, if you're going to use corner point coding, you commonly have a reference cell with k-1 levels of the factor turned into converted to transformed to binary vectors. And then, however, for output discrete categorical variables, you don't use k-1, you would use k or p, the number of levels involved. So we have 2 continuously scaled outcomes selected, categorical predictors, and then several continuous variables. So we'll click on apply. Now we haven't run that, so Explorer always, in about 5 seconds, it always determines whether you have the data. So the workflow lines are all green now, so it's ready to do a run. Now there are 2 ways that you can perform a run in Explorer when you have a series of icons in a workflow. The first is to click the execution run button here. Or second, you can single these out and right-click on them and run this. So I'll run the linear regression model now. And it's already run, so you can see the coefficients here. You can see also the recoding that was done. And if we go back to the workflow, if you want to run the multivariate normal regression by itself, just click on Run, and it's already run. If you wanted to run the boosted linear regression, you could say Run, and it's already run, and you can see the boosted results here and the goodness of fit. So to run the entire workflow, just click on this Run, and we'll select that. And then you can see the linear regression is run, and then the boosted, and then the multivariate linear, and then the boosted. Now if you switch these up and run it, so you'll get let's do this. In fact, let's make the multivariate normal icon the top icon, and then the MVA. Let's set the multivariate normal runs on the top. So whatever's in the top for the run icons will be run first. So let's run now. So the output is going to be first for the multivariate normal regression, followed by the multivariate normal regression, boosted variant, and then linear regression, and then the boosted linear regression. So let's run that. And here's your MVN reg that was run first. followed by the boosted NVN reg, and then the linear regression, and then the boosted linear regression. So the nice thing about this is if you want to change, if you have several run icons, green icons coming out of a feature selection icon, you can swap these out in terms of the vertical, and then the topmost is the order in which they'll all be run. Okay, so let's look at these outcomes now. Let's go back to the start. For the linear regression, there's a missing analysis that's done. There are no missing in this data set. Now, for the multivariate linear regression, Explorer always runs univariate linear regression first, and then it doesn't include the constant terms in any of these outcomes. So these are essentially a list of the regression results for all the univariate regressors. And then you can change the colors in the default preferences. And then green here represents a p-value less than 0.25. So we're using a cutoff threshold of 0.25 for less equal than to enter the full variable model. So then anything in red won't be entered because its entry p-value is not less than 0.25. So we're selecting candidates here. And then you're not going to get, you can see that there would have been 1, 2, 3, 4, 5, 6, 7 regressors in the multivariate table. However, we have switched on to only show variables that are significant in the end model. So if you go to Preferences, General Default Settings, and go down here, you could set the p-value, Model Building Strategy Table p-value, to 1. This is the threshold for moving predictors as good candidates from the univariate regression into the multiple regression model. And then this is the p-value threshold to show something in the multivariate normal regression. And depending on where you come from in terms of training, I started out with graduate level statistics at University of Michigan, and we were always taught or trained to report the full model. But when you get into clinical science and clinical medicine, a lot of clinicians, that is MDs or doctors, will simply say, I just want the significant coefficients in the multivariable table. So you could set this to 0.05 if you did that. And then the question that comes up is, what would, if you only selected variables that are significant in the multivariable model and then report those, if you reran only those variables again as a multivariate and not everything, would the model be the same? Well, the answer is probably, but you never know. You can never really, for multivariable models, you can never really predict what the outcome is going to be, because the variable, it's all based on correlation with the dependent variable and variance explanation. So they all kind of swap. They compete for the strongest correlation and strongest variance explanation with the outcome variable. So you can never really say, you can never really predict or state what will happen with a multivariable model until you run the model and find out what happens. So let's apply this. We now can then run, we can go back to the workflow, we just happen to have these switched up. This is going to be down here, this is going to be here, and then the multivariate normal run is here. So back to where we were in the beginning. And now let's rerun the multiple linear regression model. And here we are. Let's look at the coefficients. Now in the table, we can see that there are all the predictors that were entered. So let's just check this. There are 1, 2, 3, 4, 5, 6, 7 predictors whose univariate p-values are less than 0.25, and they're entered in the model. So in addition to the constant, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, why did that happen? Because you have to always enter all of the levels in the categorical of a categorical factor when you're running k-1 predictors of a level, because you would erroneously change the reference cell if you only entered just level 2 or level 3. So they're always added into the model. That's that's something that you really need to be careful about. So here, what am I saying again? If you have these binary predictors that are recoded from k-1 levels of the factor, and then you use just one of them, you've defined, if you only use one of them, then you're dropping level 3 into the reference cell because you're only using the binary vector that picks off level 2. So if you enter that variable into a model and employ that for your multiple linear regression, everything other than records that are in observations that are in the level 2 will be level 3 and level 1. So you've just changed the reference cell, and that's not advisable. That's erroneous, and you shouldn't do that. So Explorer, this is kind of a trick. You really need to be careful with multiple linear regression models when you're recoding into binary for categorical predictors. So Explorer will forcefully include all of the levels of the factor it won't automatically clip those out because you'll screw up the reference cell. If you really did that, you'd be destroying the definition of the reference cell, which is level 1 out of a k-level categorical predictor. And in fact, you need to really use all of the other levels so that you don't make the mistake. So if you ran this for the smoking stat, you can see the smoking status 3-level categorical variable and the vitamin use 3-level categorical variable only had their level 2 binary vectors 0, 1 used that would be moved forward. So if you did that and then reported these coefficients or said it was significant or not significant and then reported those coefficients, it would be erroneous. You'd be violating, it would just be erroneous. You would just be wrong because you didn't alter, you didn't change, you didn't drop records for the 3rd level. So if you have a 5-level categorical factor and you want to use those in like an ANOVA, which is essentially is regression, and you create the binary factor, you recode and create the binary factors for levels 2 to 5. And then you come along and find out that only the level 3 binary vector is a significant predictor of the outcome, and then you use that. You've just screwed up or erroneously changed the assumption for what the reference cell is. So if you use the 3rd level binary vector from a 5-level factor that uses 4 binary vectors, k-1, 5-1, and you just use one of those, you've just altered, you've made an erroneous use of that binary vector, because if you use the level 3 binary vector alone, everything else is going to be the reference cell will be levels 1, 2, levels 4, and level 5. And you didn't want to do that. So you have to really be careful with that. So Explorer will not let you make that mistake. So let's look at the results of the multiple linear regression run. We can see that the F statistic is significant because the F is about 7.2, and then the null F, the tabled lookup F, is 1.9. You have your sums of squares for regression error in total, the degrees of freedom, and then your mean square errors, and then your multiple R, the R squared, and then the root mean square error. And in your multiple variable regression table, you have everything that was used. Why? Because we set in preferences, we set this value to 1. This value is the p-value threshold used for entering univariate predictors into the multivariable model as candidates, and this setting is the p-value cutoff for reporting coefficients in the multivariable model table. So you have your variable names, the coefficients, the standard errors. Obviously, the z or the t for large sample runs is equal to the ratio of the coefficient to its standard error. And then the tail probabilities, and then the 95% confidence intervals of the coefficient values. And then there's a color that's ascribed to p-values less than 0.05. So I would report all of the coefficients in the full model run. And then you also have a table of partial correlation coefficients. Now, Explorer will also remove outliers. So if you want to look at the outliers for this run, we turned off, if you want to look at the residuals, they're here. So Explorer, the outlier values are shown here in the residuals, and there are a number of different types of residuals used. So the residual here is just E, it's the delta, it's the difference of the observed Y and the predicted Y, the Y hat. You have the standardized residual, the studentized residual, the deletion residual, Cook's distance, the leverage, which is the diagonal of the n by n hat matrix, and the DF fits. And then Explorer gives a pretty nice indication of what the criterion are for each one of these residual types. So anything that's red here is an observation that's overly influential on the model, and therefore Explorer will pull these and rerun the model without these records automatically. The variance inflation factors, as you know, the default criterion is commonly 10. And then it shows based on N and P. A lot of these are based on the parameters P and N for the regression. And then it will actually just calculate what they are. So then you know if the deletion residual is greater than or less than 1.65, you'll see it'll be highlighted in red. So these are bad observations. And then Explorer will rerun the model with the outliers removed. So you can see there's 314 here, then there were 293 with outliers removed. And it's a pretty nice feature. So then you can go through the results and determine how much the coefficients changed, or whether or not the coefficients that were significant changed. Here, based on the colors, they didn't really change. So those are pretty nice features of the multiple linear regression models. For the boosted linear regression, we have the following outputs here. So let's click on the plots for the boosted linear regression, and we can see here that as in terms of the number of steps used in the boosted regularization with the coefficient values shown here, you can see that various variables are entered into the model. So the most important predictors are going to be these. This is a negative coefficient. So the most important predictors are going to be the ones for which they're non-zero early on in the steps of the algorithm, and then the later ones will come in. So this is a report of the regression coefficients versus step. And then if you want to click on the gradients, the norm of the vector of regression coefficients versus the values themselves, obviously as the coefficients increase in terms of the steps taken, it's another way of looking at variables that are most important. So this would be the vitamin, this is the third level of the vitamin use variable here. And then this lighter blue, this is age that comes in second. And then a few of these come in early on, but they're a little bit lower. And then these dark blue, so likely this one, yeah, there aren't any other dark blue. So the second sex binary vector came in. And then if you want to look at the goodness of fit for this model, it fits because for cross-validation at about the 29th step, it gets lower. So when you're looking at boosted regression results, you'll always see when cross-validation is performed, you'll always see that they will go up after the goodness of fit. The root mean square error does go up after, either for lasso or for the number of steps or the iterations in a stepwise boosted algorithm. So the model fits. And then if you want to look at coefficients, you can see here's the norm of the entire vector of coefficients. And then the constant term, you're really not interested in this in a boosted regression run, but you can see age, kettle. Now if you want to color these as you go by, and then we'll just drag them over here. If you want to color, you can determine in terms of the magnitude of the color which variables pretty much come in are first. So I would probably go within each column and color these rather than all of them. So let's do that, because relatively speaking, we'll look at this both ways, and then you can see if they go up or down. Well, for all practical purposes, yeah, let's continue to do this. I didn't go all the way to the end of that, so let's highlight that. Take the third fiber variable, color that, and then the fourth cholesterol variable, color that. It's pretty low at the beginning, but it turns out to be negative. Same color scheme. And then sex, this is going to be a real high red value. And, well, let's go back and color all of them with the same scale. So we see that the majority of these are all pretty low. The second gender category is a little bit higher, but then relatively speaking, the fiber variable really is much higher than any of these. So fiber goes up first, and that's followed by, now these are negative, so actually in terms of magnitude, the vitamin use really kicks in, and then smoking kicks in. They're negative, so they have a negative effect on the outcome variable. And then fiber is important as well, and then gender, there's a gender difference too. So let's look at a negative coefficient for vitamin use coming in here. It's real strong. And then let's look at fiber ramping up. Let's not save that. Yeah, here's vitamin use coming down, and then fiber coming up, but its magnitude. So it started early, but in the steps, but its magnitude is not really that high. So it would be important. So you'd want to focus on fiber and then vitamin use. That really had a significant effect on it. Was beta plasma, which is the dependent variable. And we saw gender, which is this real dark blue come in here. So it had a higher coefficient. So it's kind of a trade-off. You want to look at the magnitude of the regression coefficients versus what comes in as the most important. Now, if you click on this coefficient, the minimum step, it'll show you the values of the coefficients at the cross-validation goodness of fit where the model best fits. And these would be the coefficients that you would use. Now for either the lasso or for boosted regularization based on a stepwise approach, it's difficult to determine the variance-covariance matrix because it's not really straightforward linear regression. And Explorer has not been developed to report the variance-covariance matrix for its regularized form or variant of a multiple linear or multivariate normal regression or logistic regression or Cox as well. So you would use these variables, you would report these variables at which represent the vector of coefficients at the minimum step in the cross-validation goodness of fit model. Next, let's go over the boosted multivariate or the multivariate linear regression results. So MVN is here. You have missing the full model test, so Wilkes lambda Pillai's trace, Lawley Hotelling trace, Roy's greatest root are all multivariate tests, and they're all significant for this model that we ran. And you have feature tests, so those same 4 against the features with the degrees of freedom and then the p-value, which commonly are the same for all features. Now for the regression coefficients, you will get a table for each dependent variable, and we had obviously 2 dependent variables, the first of which was beta plasma, and then the second was retinol plasma. So plasma concentrations of the research subjects for beta carotene and plasma concentrations of the research subjects for retinol in the blood. So looking over the coefficients, they're pretty straightforward. You don't have a univariate approach here with multivariate, rather all of them are used. And then you have a list of significant coefficients that came out for which the p-value criterion is used again. But again, here you can see variables that are not significant predictors are all reported. Okay, so that's it for the multivariate normal. You'll get a table for each dependent variable used. There were 2 here, so there's 2 table outcomes. Now for the boosted MVN regression, let's look at the plot. So this is with the beta plasma as the outcome variable. So the majority of these predictors were all pretty important. There are several stragglers that really didn't do much here, but they all ramped up in importance in terms of the coefficient values. And then they didn't change that much. And then for the other dependent, and then if you look at the norm of the regression coefficient. Now remember this regression coefficient vector has 2 columns. It's not a p by 1, but it's a p by 2 now. But we're still only going to use the regression coefficients with respect to this predictor. So that's essentially one of the columns in the 2-column coefficient array or matrix. And then it's a little bit more advantageous to look at the norm versus the coefficient values by themselves because it tends to show you kind of like a linear rather than a nonlinear type importance as a function of the regression step in the boosting. So again, quite important here. And you can see vitamin use is important first. And then this dark blue is going to be gender coming off here. Now let's go to the other dependent variable, plasma retinol concentrations. Pretty much the same thing, but the coefficients are different. Again, you can hunt them down. You can see a little bit different. And then smoking status came in here in the light yellow. Let's look at the other dependent for this. Yeah, smoking status, you don't see that here. So for the other dependent variable, smoking status becomes pretty important after near about 30-some iterations in the boosting. And then obviously in boosted regularization and also in lasso, you can see that coefficients become more important at any point in the steps. Lasso doesn't really use steps, but rather has a beta coefficient that is like the strength of the lasso that you're using, and then you essentially plot coefficient values as a function of the beta or the alpha. I think it's the beta, and then variables will become less important as a function of boosting, while other variables can become more important. So this blue line here is a negative coefficient that became less important later on in the iterations, and then this other blue line is a regression coefficient value that's also negative that became more important because it became more negative. So more negative is in terms of the step functions or iterations, and then more positive here. So positive regression coefficients and then negative. So that's it with regard to a workflow for regression, the linear regression forms of regression that Explorer will handle. We went over multivariable or multiple linear regression using straightforward single outcome y-value type models, and then the same for the boosted form. And then for the multivariate normal regression, we selected two outcome variables, and then we also ran the boosted multivariate normal regression variant of the MVN regression model itself.